Hey everybody, welcome back. Chem 104, Chapter 3, Part 2. As promised, here's the math. Hope you got your calculator. We're going to continue talking about energy. So the last section that we finished in the Part 1 video, we introduced the calorie and the joule. We'll move that information forward into this part of Chapter 3. We'll do more calculations, and we'll use energy values to calculate the amount of energy in a given food. To do that, we use calorimeters. This is experimentally, right? So when you look at the nutrition facts, there's an energy there. It tells you how many calories is in something. And the way that's figured out is by using a calorimeter. What you have is a steel combustion chamber, which I'm outlining here. And in that chamber, you put your food sample. I don't know what type of food that is, but I don't want no parts of it. You also have oxygen in this chamber, along with some ignition wires that you can use to spark and cause a fire. Yes, you want to start a fire in here because you're literally burning this sample of food. And all of the energy that's released is absorbed by the water. So all these red squiggles, that's heat released. From your food sample. That heat is absorbed by the water that is on the outside of that steel combustion chamber. You can measure the temperature change of the water using a thermometer. You see that it's poking down into the water there. And that temperature change gives you information about how much energy was released from the food. And like I said, on food labels, you have the nutritional calorie, which is a kcal. Here's your equality right here. 1 capital C calorie is equal to 1 kilocalorie. In other countries, they actually use the kilojoule. So if you travel abroad, once COVID is over, and you happen to go to a grocery store, you'll see kilojoules, not calories. So in each food, you're going to have kind of the 3 types of food, right? You've got carbohydrates, fat, and protein. Those are the macromolecules that make up the foods we eat. Each of those has a different amount of energy per gram. The most energy dense is fat. You have a lot of energy from a small amount. Carbohydrate and fat are the same. You'll be given this information in the table if you end up needing it for the exam. And by if, I mean you will, right? Let's just be clear. But you don't need to memorize this. You may need to reference it for your homework, though. Let's try a sample problem where we have to calculate the amount of calories in a food. So a cup of whole milk contains 13 grams of carbohydrates, 9 grams of fat, 9 grams of protein. How many kilocalories does a cup of whole milk contain? Round the final answer to the tens place. So if we want to know the total number of calories, then that's going to be equal to the calories from your carbs plus the calories from fat plus the calories from your protein. I'll use different colors for these. So the carbs I'll keep in black. Fat I'll put in red. Protein will be blue. So our carbs, we know that there are 4 kcals per gram, and we've got 13 grams of carbohydrates in milk. So that's what our carbohydrates contribute. The fat, we have 9 grams of fat. So we'll do the same thing, 9 grams of fat, and then we use the conversion factor, 9 kcals for every gram of fat. The last addition we have to make is for protein, and that's going to be very similar to what we did for the carbohydrates, only we have 9 grams of protein. So when you're doing this on your calculator, you want to get an amount for the carbs, for the protein, and the fat. You want to add those together and use the rules that they tell you for rounding. So 169 kcal is what you should get when you total all of this up. And then it says round the final answer to the tens place. There's the tens place. Look at the 9, it's 5 or more. So we increase that 6 to a 7. Our answer is C. We'll do more practice like this in class just to make sure that you get it. But you need to know how to use conversion factors if you're going to get these types of questions correct. The information from Chapter 2 on equalities and conversion factors is key to being able to do a lot of the math that we're going to do from here on out. Again, if you have issues with it, please reach out. Don't just suffer in silence. Don't say, well, I'll just make it. No. Reach out. That's what I'm here for. So we're talking about energy. Energy in food. We talked about kinetic and potential energy in the previous video. Now we're going to talk about specific heat. We can use specific heat to calculate the amount of heat something gains or loses. Specific heat is different for different substances. So water has a specific heat of 4.184 joules per gram degree Celsius. Metals have different specific heats. So that is something that is a property of each substance. The specific heat is the amount of heat that raises the temperature of exactly 1 gram of a substance by exactly 1 degree Celsius. And the units for specific heat are either joules per gram degree Celsius, which is the SI system units, or calorie per gram degree Celsius in the metric system. And that's little c calorie. The equation for calculating specific heat, which is abbreviated SH, is the heat divided by the mass in grams times the change in temperature. And the change in temperature is in Celsius. For water, you have 1 calorie. That's the amount of heat that is required to raise 1 gram of water by 1 degree Celsius. That's its definition. And we know that 1 calorie is equal to 4.184 joules. So this is information that you should know. It'll be provided for you, but you need to understand where it comes from. This table has specific heats for some substances. So you can kind of see the difference. There's some metals and some other compounds. Kind of relative, metals have really low specific heat and water is kind of high. That kind of thing. Now let's think through a little bit about specific heat, and we'll do a couple of conceptual learning checks. When the ocean water cools, the surrounding air does what? It cools, warms, or stays the same. If the ocean is cooling, let me draw a picture. Here's some waves. That's the ocean, right? And we've got, when something is cooling, that means heat is being released. That heat is being released into the surrounding air. That means the surrounding air is going to get warmer. Sand in the desert is hot in the day and cool at night. Sand must have a high specific heat or a low specific heat. Well, what does that really mean? If something can change temperatures pretty readily, like sand, it can get really hot and then at night, bam, it's cold. It must not require that much energy to change the temperature. And what specific heat measures is how much energy does it take to increase the temperature of 1 gram of substance by 1 degree Celsius. The more energy it takes, the higher the specific heat. Since sand changes its temperature pretty readily, it must have a low specific heat. It doesn't require a lot of energy to increase the temperature of sand. If these two conceptual questions don't make sense to you even after the end of live lecture, again, come find me. I am available. Now, we're not just going to talk about specific heat and conceptualize. We got to do some numbers. When you're calculating the amount of heat gained or lost, you also need to have the mass and the temperature change. So heat is always equal to the mass times the temperature change times the specific heat. And you can rearrange this equation if you need to solve for specific heat or something like that. Or you can solve for the temperature change, all of that goodness. Remember that specific heat can be in calories per gram degree Celsius or joules per gram degree Celsius. Same thing, it's just different units. Let's try a problem. What is the specific heat if 24.8 grams of metal absorbs 275 joules of energy and the temperature rises from 20.2 degrees Celsius to 24.5 degrees Celsius? Okay. What we know is that heat is equal to the mass times the change in temperature, that's delta T, times the specific heat. The question is asking for the specific heat. So we need to rearrange to solve for the specific heat. We're going to divide both sides by mass times delta T. And when I rewrite that, I'm going to write it in a different color so it stands out. Specific heat is equal to the heat divided by mass times delta T. Let's make sure that we have all of our components. We need to know the heat, the mass, and the delta T. All of these things should be provided in the problem if we're going to solve for specific heat. The first number we encounter is 24 grams of a metal. That's a mass. 24.8 grams. Absorbs 275 joules. We know joules means energy, right? It says of energy. 275 joules. That's our heat. The temperature rises from 20.2 to 24.5. The change in temperature is the difference between those two. So the final temperature minus the initial. And when you do that math, you should get 4.3. Now that we've got all of this information, we can plug it into our equation for specific heat. That's the math that we're doing. And notice that we've got joules, grams, degrees Celsius. So always look it over and make sure that your units are in the right spot. When you put that into your calculator, it's going to give you a bunch of digits. But we have to think about sig figs. 24.8 times 4.3, that can only yield 2 sig figs because our temperature change has 2 sig figs. Our final answer is 2.6 joules per gram degree Celsius. Don't forget the units of specific heat, or else your answer is wrong. We talked about the states of matter. And when we talked about physical changes and physical properties, we were talking about changes of state and things like that. We can do calculations, and we can also use terminology to talk about the changes in state among solids, liquids, and gases. I'm going to go through some of these a little bit quickly just because I know y'all already know it. You've been living life for a while. You know what melting and freezing is, right? But to make sure that it's all covered, I will cover each of these terms. First, we'll start with melting and freezing. Melting happens when you're going from a solid to a liquid, and you're at its melting point. Freezing, you're taking a liquid, you're making it into a solid at its freezing point. Water has a freezing point of 0 degrees Celsius. So if you've got a solid and it's at 0 degrees Celsius, it's going to start melting. If you've got liquid at 0 degrees Celsius and you are cooling it, it's going to solidify. Melting and freezing are reversible. Sublimation, this is one that you may not know. When the particles on the surface of a solid change directly to a gas, that's sublimation. There's no temperature change involved. It just goes from a solid to a gas. The opposite of that is deposition. Gas particles, bam, change into a solid. Dry ice, which is solid carbon dioxide, undergoes sublimation at minus 78 degrees C. So all is fine and dandy. You've got carbon dioxide as a gas. It's hanging out. The particles are zipping around. And then all of a sudden, at negative 78 degrees Celsius, boom, you've got a solid. Now we'll talk about evaporation, boiling, and condensation. Evaporation is not a change of state in the way that boiling is. Boiling, we're taking all of our liquid and it is all going to become a gas. Evaporation is just on the surface. So it's the molecules on top, the water molecules on top of that pot of water that isn't really boiling yet, but you see the little wispies of steam. That's evaporation. Eventually, and you may not even see that if we be completely honest, but if you just leave water out, eventually it's going to be an empty pot or an empty cup. That's evaporation. When you have gas molecules of water, we're using water as an example, come together and they form that liquid, on the outside of your cup or something like that, that's condensation. So gas molecules lose energy, they slow down and form a liquid. When you have boiling, we're talking about all of the water molecules have the energy to form a gas. Evaporation is just the ones at the surface, but boiling, which is, a real change of state, is forming a gas from all of the liquid molecules. This is a chart that you can fill in yourself with all the different terms, freezing and melting, sublimation, deposition, and you can include an example of solid, liquid, and gas. So one example that you could use is what happens to water. You've got liquid water here. The solid is ice, and the gas, water vapor or steam. You write in on top and on the bottom what the name of the process is. So if you're going from ice to water, you're melting. If you're doing the opposite, you're freezing. So use this to practice all those terms and know the relationship between all of them. Moving on to talking about heat of fusion and eventually heat of vaporization. What these terms do is we're talking about the amount of heat that is released or needed for a change of state. With the heat of fusion, we're talking about the amount of heat released at its freezing point or the heat needed to melt at the melting point. So remember, freezing and melting, they are the opposite of each other. They need the same amount of heat. With freezing, you're releasing that heat. Melting, you require that same amount of heat as input. To melt water, you need 80 calories per gram, or 334 joules per gram, to go from a solid to liquid. If you want to freeze water, that much energy will be released. When you're adding energy, that's an endothermic reaction. So energy is required. When you're releasing heat, like in the case of freezing, that's called exothermic. To calculate the amount of heat to melt or freeze water, or any other substance that you have this information for, you simply take the mass in grams and multiply by the heat of fusion, which is going to be in calories per gram or in joules per gram. Heat of vaporization, we're talking about going between boiling and condensing. When you're boiling a liquid, 1 gram of that liquid going from liquid to gas, that will give you what the heat of vaporization is. Conversely, if you condense some gas to liquid, that 1 gram of gas, that is going to happen to condense, and it's the same amount of heat released as what's needed to absorb and make the gas. It's kind of circular, but once you start practicing it, you'll understand how they're related. So the heat of vaporization for water, we're talking about 540 calories per gram, or 2,260 joules per gram. So much more energy here for the heat of vaporization than for the heat of fusion. In this first equation, we've got heat being added, right? So plus energy. That means it's endothermic. In the bottom, we're talking about condensing the gas to a liquid. That's releasing energy. and that's called exothermic again. Let's do some math. How many joules are needed to melt 32 grams of ice at 0 degrees Celsius? The heat of fusion for water is 334 joules per gram. And our equation is right here. The mass of water that we have is 32.0 grams. The heat of fusion, which is what we use for melting and freezing, there it is. We've got grams in the numerator and grams in the denominator. That means that we've got joules left as our unit. When you're entering this into your calculator, you'll do 32 times 334. That's what your calculator will tell you. But we know better. We need to use significant figures. And our mass, which is measured, has 3 sig figs. That means we need to make this into 3 sig figs. We've got 2 choices. We can round here. When we look at the 8, that increases to increases the 6 to a 7, and then the remaining places become a 0. Remember that those are placeholder zeros. You can also write this in scientific notation. Either answer would be correct. Now let's do this with kilojoules. We've got 50 grams of steam being released from a volcano at 100 degrees Celsius. Oops. Sorry about that. We've got grams in the numerator, grams in the denominator, left with joules. You multiply everything out. You get a lot of joules. But if we left our answer there, it would be wrong. Why? Because the question asked how many kilojoules, and right now we just have joules. We take our joules and we need to convert to kilojoules. Remember that kilojoules, kilo means 1,000. There's our final answer. Always be sure to read the question, because if this answer was present on a multiple choice exam and you chose it, it would be wrong, even though you did the calculation correctly. You just didn't answer in the correct units. So be careful. Always refer back to the question. Make sure that you're answering all the parts. We're not going to do calculations for sublimation and deposition, but just know that sublimation is actually used to prepare freeze-dried foods. The water vapor changes to a solid on contact with a super cold surface. Freeze-dried foods have a long shelf life because they don't have any water. We've been talking about changes of state, solid, liquid, gas. We're going to put all of those concepts together and look at heating and cooling curves. So this is a heating curve. We've got heat being added on the x-axis. And on the y-axis, we've got our increasing temperature in degrees Celsius. Let's say that we're starting with water and we wanted to do a heating curve. Well, at really low temperatures, water is going to be ice. It's going to be a solid. As you put heat into it, let's say you left out that ice on the countertop, it's going to slowly warm up. So that's our increase in temperature until it gets to 0 degrees Celsius. That's the melting point. When you are changing phases or changing states from solid to liquid or liquid to gas, when that conversion is happening, there's no temperature change. You'll also notice that on here, when there's a change in state, it's a plateau. No temperature change. We've got the change of state occurring. Once all of that solid ice is melted to water, it will continue to gain energy. It's going to absorb heat from the environment. The temperature is going to go up. We're adding heat, remember that. Once you hit the boiling point of 100 degrees Celsius, you will again have a change of state and a plateau. Then you have gas, and you can continue to heat that. So the plateaus on this curve means a change in state. The slope means that you have a change in temperature. A cooling curve is the opposite. If you start with something like steam, that's gas, right? It's at a really high temperature. And you start to cool it down until it gets to 100 degrees, which is where it's going to condense. Remember that those plateaus are changes of state. Once all of that steam is water, it will continue to cool. It's going to continue to release heat until it reaches the melting point. That's 0 degrees. Then you're going to hit another plateau where all of the water is turning to solid ice. When that happens, all of that ice will just keep getting colder and colder. We're describing the same changes in state. We're just looking at it whereas we're cooling something that's really hot versus heating something that's really cold. We can do calculations based on what's going on with these heating and cooling curves. Calculate the total heat in joules needed to convert 15 grams of liquid ethanol at 25 degrees Celsius to gas at its boiling point of 78 degrees Celsius. And then we know the specific heat and the heat of vaporization. Before we start doing the math, let's sketch a quick curve. We've got liquid ethanol at 25 degrees Celsius. Let's say that's here. Always have to label our graph, right? So that's 25 degrees Celsius. We need to get that liquid ethanol to 78 degrees. Then it needs to go from the liquid to steam. Let me change colors here. We've got liquid ethanol here. Liquid plus gas there. And just gas there. For the slopes, where we have a temperature change, you're going to use specific heat to calculate that. At the plateaus, we'll use the heat of vaporization to calculate how much energy is going into that liquid ethanol to make it gaseous. So our total heat is going to be our heat calculation with specific heat plus the heat of vaporization. With the specific heat calculation, remember we said heat is equal to mass times change in temperature times specific heat. We already have all of those things. So our heat calculation, the mass of the ethanol is 15 grams. The change in temperature, we've got 78 degrees Celsius minus 25 degrees Celsius. Need to put all my sig figs. That's the wrong color green. My bad. Much better. So there's our mass, our delta T, and our specific heat. We're told it's 2.46 joules per gram degree Celsius. Now I need to handle that heat of vaporization. Heat of vaporization, we've got heat is equal to, I'm going to put heat VAP times the mass. Mass, heat of vaporization. When you do that, what you need to do is do the calculation for specific heat, get a number for that, and then you get a number for the heat of vaporization calculation, and you add those together. That's the number that you should get, but we still need to consider sig figs. And that's the reason why you want to do these two calculations separate. You have 3 sig figs in all of these. You've got 3 sig figs here and here. When you add them together, you're going to care about the number of places, decimal places, right? So that's why you want to make sure to have each piece and then do your addition. A little bit lengthy on this, but I want to make sure that you get it. We're going to do another example, and we'll do more examples in class. When a volcano erupts, 175 grams of steam at 100 degrees Celsius is released. How many kilojoules are lost when the steam condenses and then freezes at 0 degrees Celsius? I always recommend drawing out what's going on. This time we're starting at a higher temperature and we're releasing heat. So this is a cooling curve. We're starting at 100 degrees Celsius. And that will condense. That is a change of state, so that's a plateau. To go from there all the way down to 0 degrees Celsius, that's a slope part. We're just slowly releasing heat, releasing energy, and that means a decrease in temperature. Then we form ice. That's a plateau. Whenever you see a slope, you calculate the heat with specific heat. Whenever you see a plateau, you calculate that with the heat of vaporization, like in the case of condensation, or heat of fusion, like when something is melting. So the total heat is going to be the heat of vaporization. We're going to do that calculation plus the specific heat calculation plus the heat of fusion calculation. Heat of vaporization, we just need the mass, which is 175 grams, and multiply by the heat of vaporization for water, which is 2,260 joules per gram. For the specific heat, we need the mass times our temperature change that's 100 degrees. Remember, there's 100 degrees between condensation and freezing. And then our specific heat of water. The last piece is the heat of fusion. And that's taking the mass times 334 joules per gram. You get the number for each of these pieces and you add them together. Notice that there are two placeholder zeros there. But we have to look back at the question again. The question is asking about kilojoules. So that means that you have to divide by 1,000. We also need to make sure that sig figs are correct here. So you should get 528 kilojoules. Again, we'll do some examples in class. We'll practice drawing the heating and cooling curves, and then also finding the answers. Thanks for watching. Make sure that you tune in for a live lecture for practice problems and all the details regarding assignments and exams. Stay safe.